Day at this college, and it's such a pleasure to be here talking about data structures and algorithms. So that is literally one of the favorite things I love talking about. And it's again such a pleasure to be the part of this society. And I think it will be a good continuation to what we had yesterday. So I did receive the feedback from yesterday's session, and today I would like to do a little bit of, make some corrections. So yesterday I had a feedback which told me that the students had some sort of expectation that I also explained the topic before moving towards the solutions. And today I'll be doing exactly that. So today also I have a set of questions which all of us will be solving together. And before I solve these questions, I will also be trying to explain the topics to you so that you have a better idea about this topic in the first place. And then we can all move ahead and then see how we can solve the question that I have for all of you. All right, so moving ahead, I will be sharing my screen just like last day. And you have to tell me when you can share my screen. Okay, so sharing my screen, just a moment, please. Not sure, where is it? Yep, this one, I guess. Yeah. Can you guys see my screen? I'll have to increase the font size again this time. Just let me know when you can see it. Okay, I can see people writing in the chat box that's visible. Great. Let me just change the font size to last day so that it's very clearly visible to all of you. Settings. I will have to. There's something wrong. Just 1 second. Parents. Let's make it 18. Good. Yeah, this should be better. Is it? Can you guys read it? Is it clear? This is just some normal Java code that I was working on one of the projects that I was creating. All right, so moving ahead, just 1 second, allow me just one moment. I think there's something wrong with my system. Just a second, please. Yep, it's all fixed. Where is it? Share screen. And here we are again. Okay, let's move ahead. So these were the 3 questions we did yesterday. Today we will be moving ahead and we will try to see a few more questions. So today I have a few questions on linked list. So let me just create that question, or let me just create a class called, okay, let me just create a class called test. So this is my class test, and let me just explain what a linked list is. So a linked list. So a linked list is a data structure which is very much similar to array. So what happens in an array? In an array, we usually have something like this, right? 1, 2, 3, 4, 5. This is an array. Yes, no? This one, 1, 2, 3, 4, 5. This is an array, right? Any feedback? Yes, no, anyone? This one is an array, right? Yep, it is an array. So what happens in a linked list is that linked list is also very similar to array, but to explain linked list in a more better way, I would say that it is more similar to a railway. It's more similar to a train. What happens in a train? There are compartments, there are bogies that we call them. So compartments, then there's a train engine, then a compartment, then compartment, then compartment. So every compartment is linked to its next compartment. Right, every compartment or every bogie is linked to its next compartment, and then there is the last compartment of the train which is linked to nothing. Isn't the train like that? Isn't train exactly the way I'm explaining it? There's the engine, and then there is a compartment, and that compartment is linked to the next compartment, and then the next compartment, and then the next compartment, up until the point that we have reached the last compartment. So the last compartment is not linked to anything. So kind of we can say that in the last compartment, we see that there's an X written, right? So we can say that it's kind of linked to X. So in a linked list, if we had to store the same data which is present over here in a linked list, it would be something like this. 1, which is linked to 2, which is then linked to 3, which is then linked to 4, and which is then linked to 5. Something like this is called a linked list. Okay, and today we are going to exactly work with this, that is linked list. So today I will be telling you about how to reverse a linked list. This is one of the easiest questions on linked list, and it's going to be something which is interesting for all of us. So I'll rename this class. Let me just rename it. Reverse REVERS reverse linked list. Yep. So now this is what we understand from linked list. Is the concept of linked list clear? Of what do we understand from linked list? Is the concept of linked list clear? Okay. For people coming in from languages such as C or C++, when you create a linked list on your language, that is C or C++, we use the concept of pointers there. But in Java, we don't have pointers in the first place. There are no pointers in Java. So in this case, creating a linked list in Java might be a little bit different for you to understand. It might be a little bit difficult for you to understand, but the logic is exactly the same that you apply in C++ as well as you apply in Java or any other language. The only difference is that at the time of creating a linked list in Java, we will not use the concept of pointers because Java does not have pointers. It doesn't have pointers at all. So let's move ahead and try to reverse a linked list. But for that, for reversing a linked list, we need, what do we need? We need to understand how a linked list is created. So let's start and try to create a linked list. So in a linked list, what happens is that a linked list is like a template. A linked list is like I said, a linked list is like a train, right? So a train has compartments where every compartment is connected to its next compartment, right? So in case of linked list, these are the compartments, right? 1 is a compartment, 2 is a compartment, 3 is a compartment, 4 is a compartment, and 5 is a compartment, right? So every compartment contains 2 types of information. The first information is the data that it contains, in this case 1, and the second type of information is what is or which compartment it is connected to. So the first compartment contains 2 types of information. The first information is number 1, that is the data that it contains is 1, and the second information, that is the connection, or which we also can say as next, is this entire compartment. This is how linked list is created. So in the language of linked list, every train compartment is called as node, N-O-D-E, node. So in case of Java, it will be a class node, or we can also write it like this, or we can also write it outside it. So I'll just create a static class node and let's start writing questions. So there will be one data, int data, which will be nothing. And then there will be another node, which will be called next. Is this part clear? Why are we going like this? Yes, no, anyone? If no, then I'll try to explain it one more time. Anyone with any sorts of queries or questions? Okay, that's great. In case of C++, here only we use a pointer, something like this. I don't know, I'm not sure about the syntax, but this is how what we do it, which basically means that we are pointing towards the address of the next node. Address of the next node. That is what we do in C++. In Java, unless you create a new object, there is always pass by reference. So it is also pointing towards the address of the next node, but it just does not look like how we do it in C++. Bhavya asks me, why are we using static? We are using static because all of this context will be called inside a main method, which is static in nature. So that is the reason why we are using static over here. So this class needs to be created at the same time that the main method is called. So that is why we need to create a static class node. If we don't create static, we will have issues in using this class inside the main method. That is the only reason. Okay, so let's move ahead. So this is our node class. Let me just create a constructor for it. Public node int data and then node next. Then the constructor will something be like data is equals to this dot data. Oops, I'm making it in the wrong place. I should make it inside it here. This dot data and then this dot, sorry, my mistake, which should be this dot data is equals to data, and then this dot next is equals to next. This is our constructor. Now we can easily take user type inputs and create a linked list. Now let's see how we can create a linked list. Okay, so let's create a main method, pspm. This is our main method, which will be used to run. Okay, so let's create a linked list. So let's create the first linked list. So we will create a new node. Okay, let's take 1 and then the second node, which is again a new node. which will be 2, then new node, which will be 3 comma new node, 4 comma new node, 5 comma null. Is this line clear to you? Did you guys understand what is happening over here? This one, this line number 19. Is this line clear? Yes, no, anyone? Okay. This line is clear, then that's great. You can see my IntelliJ is also trying to tell you what type of argument I'm trying to pass. Please explain once again. Okay, so Priyanshu, what part did you not understand? Did you not understand line number 19, or did you not understand this part? Line number 19. Okay, fine. So this is the constructor, right? This is the constructor. This is the constructor. So this is how we are going to create a node in. This is how we are going to create a node of linked list. Okay, so we understood that this is how linked list is going to look like. Okay, so the first node is going to contain two types of information. The first information is the data that it is going to contain. In this case, it is 1. And the second type of information is that what is the next node. Okay, similarly, this node will contain 2 and the next node. This node will contain 3 and the next node. This node will contain 5 or 4 and the next node. And this node will contain just 5 and nothing after that. Okay, so that is exactly what I'm trying to do here. So this is the first node, which is containing information about the second node, right? So this entire is my second node. Now my second node, which in this case is containing information about itself and the third node. Similarly, the third node is this. This is the fourth node, and this is the fifth node. Did you understand now what is happening? If you want to understand it in a better way, you can have a look like something like this. This will probably help you to understand it in a better way. Now, did you understand? Is it more clear? Anyone? Yes, no? Okay, great. So this is basically a linked list. It is a linked list in Java, and it has custom linked list. Java also provides a inbuilt linked list, something like this. List, let's say integer list is equals to new linked list. This is also allowed in Java, but this is not what we're going to do as of now. Okay, somebody's asking me to repeat it one more time. All right, Shahiba, do you want me to explain this part, or is there some other part of the code that you want to understand? Sahiba, I'm sorry to mispronounce your name last time. Which part do you, this part, right? Right, number 19, right? You can also unmute yourself if it's taking too, like if there's a communication gap. Okay, so it is line number 19, right? So we want a linked list to be created in this kind of fashion. So a linked list is going to contain nodes, and every node is going to contain two types of information. The first information is the data that it has to contain, and the second information is the next node in the linked list. That is the information that every node contains. So in this case, this node that you're seeing here, this gray color node that you're seeing here, this is the linked list, and it is containing one node, which is connected to the second node, which is then connected to the third node, which is then connected to the fourth node, and which is then connected to the fifth node. So the fifth node next is null, which basically means that it is the last node and it is not pointing to anyone. Whereas this one, the first node is containing the data as 1 and is connected to the second node. You can see the constructor. So the second argument is always going to talk about the next node to the current node. That is what we are trying to do here. So this argument is going to be the next node to the first node. And similarly, this one is going to be the next node to the second node. This one is going to be the next node to the third node. And this one is going to be the next node to the fourth node. And then the fifth node has nothing. So therefore, the next is going to be null. Now, did you understand? I hope you understood it this time, Sahiba. Yes, no, anything? Okay, great. All right. So our task is to reverse a linked list. So in linked list, what happens is that we have 1, then 2, then 3, and then 4, then 5. So now that we want to reverse this linked list, we want to reverse the connection. So we'll have to do basically something like this: 5, which is connected to 4, which is connected to 3, which is connected to 2, which is then connected to 1, and then 1 is not connected to anything. Or should I say it's connected to X. Okay, so this is what we want to achieve here. Okay, so it is going to be a little bit complicated to understand if it's your first time working with linked list. So please pay very nice, please pay attention over here. So this is what we're going to. So now that we already have a node, let me just write a function to print a linked list for you as well. So let me just write it: public static void print linked list. Okay, so this will have a node type, or should I write node head? The head means the first, or should I just write node. Okay, so this node is basically a linked list. Okay, so now that we want to print it, I'll just create a Java function to print this. While node is not. I'll explain how I'm doing this. Just allow me a moment. So I'll just write string builder dot append node dot data, append this thing. Yep. Then node is equals to node dot next, and then I will do s out string builder. Yep, this is enough probably. Or should I write dot string dot trim? This will remove any extra trailing spaces. Okay, so this is our main function. Now let's try to print this linked list that we have just created here. So let's pass node and see if our linked list has been properly created or not. Okay, so I'll run it. Running it, let's see what it prints. Yep, this is our linked list, which is correct, right? Which is correct, right? This is our linked list. Now let's try to reverse it. So for that, I'll just create a function to reverse a linked list. Okay, so I'll write public static void reverse linked list node. So now very well we understand that we just don't have to reverse the digits, we also have to reverse the connections. Is that part clear, that we also have to reverse the connections in a linked list in order to reverse it? How can we identify any visual difference in the output? Well, we can't identify a visual difference in the output with just the normal code. We can do it by trying to figure out whether the instances of type node or not. That can be helpful in that case. All right, so now that we understand that we also have to reverse the integers and also have to reverse the connection. These are the two things that we have to take into consideration. All right, so what I'm going to do is that I will use a while loop in order to iterate over the entire linked list. Like in arrays, we do know that like in arrays, we can easily find out the length of a certain array. But in linked list, it is not so easy to find out the length of a linked list. So in this case, we don't know up to what limits are we going to apply the loop, and therefore we cannot use a for loop there, and that is the only reason why we are going to use a while loop. So in using a while loop, I am going to iterate over every single node of this linked list and then going to reverse the connections. That is what I am supposed to do. So what I will do is that I will start with node current is equals to node. So I will start with current, basically means that that node where I am currently looking at. So node will basically tell you the first node. In this case, node will be 1 when we pass this node that we have created here to this function. So it will start with 1 and then 2 and then 3 and then 4 and then 5. Okay, so current will start with 1 and then will change to 2, then will change to 3, then will change to 4, and then will change to 5. Let's also keep a track of the previous node. So previous is equals to, let's say, null. Because it is the first node, technically there is no previous node to the current node that we have. And let's have a node next. So let's not define it now. Now let's try to write a while loop. While. Listen to this, have a look at this very carefully. Current is not equal to null. When current is not equal to null and we are doing something like this, current is equals to current dot next. Are you able to understand what this will do? This entire loop will run up to the length of the linked list. In this case, our length of the linked list is 5. That is what we are able to tell. But the computer does not know that the length of the linked list is 5. So what will happen here? Initially, current will start with 1, right? Because current's value is equal to node. So initially, current will start with 1. In this loop, once it comes, current is definitely not equal to null. So it will come to this while loop's body. Okay. Then what will happen is that current will go to current is equals to current dot next. So current dot next is equal to 2. This is the node that is next. So it will come here, then here, then here, and then here. And after this has been executed, it will come over here. And then, so after that, current. So when current is equal to 5, current dot next will be equal to null. So after that, this condition will fail and the while loop will not run anymore. So now are you able to understand why this condition is going to be used here? Because with the help of these two lines, we can run the loop up to the length of the linked list. Are you able to understand why are we using this type of while loop over here? Yes, no, anyone? That is the same logic I've also written over here. So, sir, what is the length of the linked list? Is it 9 because of int and nodes? Why would it be 9? It should it's not going to be 9. The length of the linked list is basically telling how many nodes are there, right? So in this case, there are only 5 nodes. So the length of the linked list is 5. That is the only reason. That's the only way we identify that the length of the linked list is going to be 5. So now that we have a way of iterating over the entire linked list, now let's write the right logic over here. So first of all, we can easily understand that next is equal to current dot next, right? We can easily understand that next is equals to current dot next. Okay. Now what happens in a swap function? What happens in a swap functions? We basically take a temp variable and then swap the two values. That is exactly what we're going to do here. We are going to take one temp variable and then swap the connection, not swap the values, swap the connection. So in the easiest language, we are going to turn the arrow from this to this. That is what we are going to do. So now next is equals to current dot next. This is very much clear. Okay. So now current dot next is equals to previous. Okay. So the next of the current element should start pointing towards the previous because we're trying to change the connection from one direction to other direction. And then the previous will become the current object. And then again, current is equals to next. Are you able to understand this logic? Are you able to understand this logic that I have written over here? Are you able to understand this logic that I have written over here? Yes. Okay. That's great. That's great then. So this is what exactly will entirely solve our problem. Okay. So now what I will do here is now node is equals to previous. So what it will do is that it will make the last node point towards the first node now, and I will just return the node. Return node. Oh, why should I even return the node? I cannot return, or I can just do it like this. Node type, and then I will return. This is a better way of doing it. All right, so now let's try and have something like this: print list, reverse linked list, node. Okay, so now let's run it. Yep, our linked list has been reversed. So I'll show you this node that we're going to get over here. So let me just show you this node. Reversed node is equals to this. Okay. Then I can just write reverse node. Okay. I will now debug the program to show you how exactly it is working. Debug. Oh, I missed a semicolon. I will debug it again. Just have a look over here. So this is our node. So the first, sorry, now it has been changed because of pass by reference. Have a look. So the first node is 5. The next of 5 is 4. The next of 4 is 3. The next of 3 is 2. And the next of 2 is 1. And the next of 1 is null. And now this basically means that our node has been reversed. Was this question clear to you? This is one of the easiest questions of linked list, and is definitely can also be asked into an interview. Sir, why to use linked list over arrays? Like arrays is a piece of cake, but linked list looks complicated. Is there any practical significance where it makes any? Yes, Anmol, it is definitely useful. Linked list in an array, what happens is that array is a very contiguous, it takes a contiguous space of memory. So when we declare an array, it is absolutely necessary for us to declare the size of the array. Whereas linked list is dynamic in nature. So when we create a linked list, we, even when we don't know the size of the linked list, we can store data in a contiguous linear fashion. That is the only advantage of linked list over arrays. So the best part about linked list is that it can be dynamic in nature. The size of the linked list can be changed however we want, and it does not waste space. Suppose if you create an array of size 20 and you are only storing 10 data values in it, then in that case you are wasting the 20 units of space. Whereas in case of linked list, you are not wasting any space in such case. Okay, so there is array list in Java and vectors in C++ also. Yes, that is true. But the only reason why you're asking this question to me is because you don't know how vectors and array lists in Java are implemented. When array list in Java is created, array list is created like an array with default size 10. So as soon as you exceed the size 10, it creates a new array list of size 20. So I'll tell you what happens in vectors in C++ and array list in Java. Suppose you create an array list in Java or a vector in C++. In case of Java, what happens is that the array list is initialized as an array with default sizes 10. So as soon as like suppose there are only 2 elements present in your array list. Behind the scenes in Java, it is taking the space 10, but it is only containing 2 elements. As soon as there are 10 elements in that array list, everything is fine. But as soon as you add another element, that is suppose an 11th element, the entire array of size 10 is copied in a new array of size 20, and then it is initialized as the new array list. That is how it works in Java, and the same logic is also followed in C++. So in this case, what happens, it is not a very preferred way of using a dynamic data structure like that. So to tackle with this kind of problem, Java has something called stream. There is something called stream is there in Java 8 onwards. So this solves the problem in Java, but I'm not sure if something like that exists in C++. So not sure about that, but this is the internal implementation of array list in Java and vectors in C++. So vectors in C++ and array list in Java are also wasting a lot of space. Okay, so moving ahead, this was one question that we just solved. Now let's look at another question. This time, this question is going to be an interesting one. I'm just thinking of what question should I be giving. All right. So are you guys familiar with the concept of trees, binary search trees? Binary search trees, anyone? No, sir. All right. Okay, let me just explain you what binary search trees are like. Okay, let me just start sharing my Chrome screen. 1 minute, please. Just a minute. Let me just share my Chrome screen. What's the problem? Share Google Chrome. Can't even find Google Chrome. Yeah, I got it. Share. Okay, can you see my Google Chrome? Yes, no? Yeah, okay, great. Let me just explain it with diagrams. So I'll tell you what a binary search tree is. What is a tree? What is a tree? In normal life, if we talk about tree, then we see something like this. This is a tree, right? So a tree has a stem. There are many roots inside the ground. So the tree is diverging into smaller parts, right? So from the stem, it has diverged into branches. After that, it has diverged into branches. It has diverged into smaller branches. And then ultimately, it has diverged into leaves. Isn't that right? It has diverged into leaves. Yes, no? Yes, no? Yes, no, anyone? That is what a normal tree is. The tree that we see in gardens and college campus, right? That is what we understand from tree. So the same logic is also applied in computer science. So what happens in a tree? So kind of, if you look at it, because stem is the, or should I say the root is that point of the tree which is connected or which is connecting itself to every part of the tree, right? So let's say to provide nutrition only, but at least we can say that the root of the tree is directly or indirectly connected with every part of the tree, right? Isn't that right? Yes, no? Or wait, let me just explain it in a different way. So let's say that this is a circle. Okay, this is a circle, or let's say this is a circle over here, and we have one more circle over here, then one more circle over here, then one more circle over here, one more circle over here, one more circle over here. Okay, so now let's start to add lines. Yep. Line. Okay, let's draw some more lines. Okay, so this, what is the structure? Now this structure, with this structure, I'm trying to highlight a tree. So when we look at a normal tree around us, what do we see? We see the root, then we see branches, and then we see the branches diverging out to become leaves, right? That is what happens. So this is like the root of the tree. I will just write the text also. Root. This is like the root of the tree. Where's the size? This is like the root of the tree. Okay, so this part, which is the root of the tree, don't you think it is directly or indirectly connected with every part of the tree? This part also, this part also, this part also, directly or indirectly? Yes, no? Right? Whereas when we talk about this part, it is directly connected with the root and it is directly connected with this, but it is not connected with this. Okay, in case of a tree, the direction only goes from the root to, like in this case, the direction of connection is only towards upside. Okay, the connection is only made in the upward direction. So imagine connection to have to be something like this kind of arrow is there. Okay, so the connection is only towards one side. So if this is a scenario, so if this is, oh, why is it so hard to work with it? Yeah. So if this is a scenario, if this is a scenario, then this is connected directly with this, and this is connected directly with this, but this is not connected to this. Right? Are you able to understand this logic? Yes, no, anyone? Yep. So this is a binary, this is an example of a tree data structure. This is how a tree data structure looks like. In tree data structure, what happens is that we start adding data values inside this data structure. Let's say this is something like 10. Then we will have some values for this also, like something like, let's say 5. This is, let's say 6. This is, let's say 3. This is, let's say 4. This is, let's say 8, something like that. So we can add values of, we can add data inside each of these nodes. Okay, so in a linked list, what was happening? If we make it like this, like suppose if I remove this and if I make it like this, if I make it like this, then only think about this node, and this node. Now, don't you think this is looking like a linked list now? These three parts? Yes or no, anyone? This is looking like a linked list, yes, no? Yep, it is looking like a linked list. So it is looking like a linked list. So the way we implement this in Java or in C++ is very much how we implement linked list as well. So when it comes to trees, the way we represent trees in computer science is slightly different. Like the tree is exactly the same, but it is upside down. Like I'll show you how a tree looks like in data structure, computer science. Computer science. Palm tree. Don't really need to see that. Computer science. Yep, this is how a tree looks like. Oh, it's opening Geeks for Geeks. Great. So this is how a tree is kind of going to look like. The image that you see on my right hand side. So this is how a tree looks like. Okay. So in case of a binary search trees, there are some certain rules and regulations that we have to follow. So what happens is that in binary search trees, what happens? There is a parent and there are children. So in this case, let me just take our example of binary search tree. So imagine that this is a binary search tree. So with binary, what do we understand? Binary means something that is only 2 in number, right? Something that is only 2 in number. That is what binary means. Yes or no? Let me take an example of this one. This is a better example. So binary means something that is only 2 in number. So in binary search trees, a parent cannot have more than 2 children. In a binary search tree or in a binary tree, a parent cannot have more than 2 children. In this case, 8 is the parent and 8 has 2 children. The first children is on the left hand side, which is 3, and the second child is on the right hand side, which is 10. Similarly, 3 is also having 2 children. The first children is on the left hand side, which is 1. The second child is on the right hand side, which is 6. Similarly, 1 does not have any children. That's all right. That is not a problem. So 1 is a leaf node. Just like in a normal tree, you cannot diverge more than or after a leaf. In a binary search tree also, the leaf or the node which does not have any children, it is called a leaf node. It's called a leaf node. So in this case, 1 is a leaf node because 1 does not have any children. Whereas 6 is one node which has 2 children, 4 and 7. Similarly, 10 has only one child. It is not on the left hand side, it is on the right hand side, which is 14. And just like that, 14 also has one child only, which is 13. Okay, so this is how a binary search tree looks like. Now is there concept of binary search tree clear? What a binary search tree is? This is what I explained as binary tree, what I just explained. A tree where there is a parent-child relationship and every parent cannot have more than 2 children. Can there always be only one parent? Yes, that is a mandatory thing in a binary tree. That is important. Is the concept of binary tree clear to you now? All right, great. Now in a binary search tree, first of all is a binary tree. A binary search tree is a binary tree. So this diagram that you're seeing on my screen, it is definitely a binary tree. But in binary search tree, there is one extra condition. That condition is that when you are having a parent and if a parent has a child, then we have to decide on which side that the child must go. For example, let's say 8 is a parent and there are 2 children. 3 is the one children, 3 is one child and 10 is one child. So technically we can also keep 10 here and 3 here. Can we do that in a binary tree? We can keep 10 on this side and 3 on this side. If we want, we can definitely do that. But in a binary search tree, there is one extra rule. That is that when you are trying to create a child of a tree, then we first see what is the value of the child. If the value of the child is less than the value of the parent, then that child always needs to be on the left hand side. If the value of the child is greater than or equal to the parent, then it always has to be on the right hand side. This is a mandatory condition that needs to be followed to make a binary tree into a binary search tree. Is this condition clear to you? What is exactly happening? The max number of child a parent can have is 2. Yes, that is true. Not more than 2. At most 2 nodes. Is it clear? Is it clear what a binary search tree is? Yes, no, anyone? I can see only one person writing yes. What about others? Okay, great. So that is good to see that it is clear to most of you. That is great to see. All right. So now I'm going to give a very interesting question. So let me just get back to my IntelliJ. Where's my IntelliJ? Yeah, this is my IntelliJ. Okay. So in a binary search tree, like I said, there is going to be 2 nodes, right? So my next question is something like this. For people who have used Java, how many people are here who are using Java? Anyone? Okay, Navneet uses Java. Okay. So Navneet, can you unmute yourself for 1 second? Just for 1 second, if you don't mind. If it is possible, no pressure, by the way. Can you unmute yourself for 1 second? Only JavaScript. Okay, no problem. Seems like Navneet cannot unmute himself. Well, not a problem. So in Java, we have a concept of something called iterator. In Java, we have something called iterator, Iterator. Iterator, what is the English meaning of iterator? Something that iterates, right? So a for loop can also create a logic of iterator. So what happens exactly? So I'm pretty sure something like this also exists in C++. For example, let us say that you have a vector of integers. If you have a vector of integers and if you want to print every element of this vector, so you can definitely use a for loop, right? But then there is a concept. Then there is a concept of iterator. Okay, Navneet has been given access to talk. Thank you very much, the panel. Navneet, can you unmute yourself now? Seems like there's still an issue. Okay, no problem. I'll wait for Navneet to unmute himself later. Moving ahead. So in Java or in any other languages also, we have the concept of iterator. So what is an iterator? Iterator basically iterates over a certain linear data structure. Okay, it iterates over a certain linear data structure, or it can also iterate on a non-linear data structure, and it prints values of this data structure until all the values are over. For example, if we create an iterator over an array, then this is basically going to iterate something like this: that first it will come to 1, then it will come to 2, then it will come to 3, then it will come to 4, then it will come to 5, and then it will check, okay, after 5 nothing is there, then the iterator will stop. That is the exact meaning of iterator. This is the exact meaning of iterator. Okay, so list like traversing the list. Yes, something like that. That's true. Okay, similarly, when it comes to linked list, again, this thing that we have written over here, this is also a logic of iterator only, kind of. This is also the logic of iterator only. Okay, so this is also the logic of iterator only. So what happens is that in iterator, for example, let us say that you have this array and you added an let's say you have this array and you asked an iterator to iterate over this array. You asked an iterator to iterate over this array. So what it will do is that it will first come to 1, then it will come to 2, then it will come to 3, then 4, then 5, and then it will stop. If you ask another iterator to come to this array, it will again start from 1. That is how it works. That is how this iterator logic is going to work like. Okay, so this is how iterator works. And my next question is very much related to an iterator only. So the next question is something like this, that given a binary search tree, I just explained what a binary search tree is, where there is a parent-child relationship. A parent can always have, sorry, a parent cannot have more than 2 children, and the rule is that the value of the left child must always be smaller than the value of parent, and the value of the right child must always be greater than or equal to the value of the parent. This is the logic of creating a binary search tree. Okay, and the question is something like this, that given a binary search tree, we have to create an iterator. We have to create an iterator, something like a BST iterator, which will iterate through the tree in such a way that it is going to iterate through the tree in such a way that it is going to give us all the values of the tree in ascending order. For example, let us say that I created a tree in this way. Suppose this is my parent node, 3 is my parent node, and 3 is my parent node. Then there is, let's say 2 is there, and then let's say there is 4. Okay, so this is my binary search tree where 3 is my parent node, and then 2 is the left subchild and 4 is the right subchild. Okay, so in this case, the ascending order of all the data values present will be 2, then 3, then 4, right? 2, then 3, then 4. This is how the ascending order will be like, right? So when you initialize a BST or iterator on this tree, it will first print 2, then it will print 3, and then it will print 4. That is the logic that we want to create. Okay, so this BST iterator that we are going to create, it should do 2 things. The first thing that it should do is that it should tell me that if there is any next smallest integer present in the tree. For example, let us say that when I'm using this binary search BST iterator, when I check for the first number, it will return me 2. When I check for the second time, it will return me 3. When I check for the third time, it will return me 4. When I check for the fourth time, it will tell me that there are no numbers left. Something like that should happen. Okay, something like that should happen. So first thing is that it should check whether there is a number available. If the number is available, then it should give me that number. That is the logic we want to create. So is the question clear? What are we going to do? Is the question clear? Yes, no, anyone? All right, great. Let's create a new class. We'll call it BST iterator. Yep. All right, so this is our BST iterator. Now let's try to work this out. So the first thing that we can do is that this time I'll create a class outside the main class. Okay, so I'll call it a tree node. So tree node. Okay, so a tree node is going to contain a data, int data, then it is going to contain, sorry, tree node, tree node left, and then tree node right. This is clear why I'm using left and right? Yes, no, anyone? Is it clear here why I'm using left and right? Okay, great. All right, let me just create a constructor for this as well. I'll just use IntelliJ, so it should be Alt, Shift, and Insert. Where is it? Where is it? Generate constructor. What of all of these three things? Okay. Yep. This is our constructor. Okay, now let's move ahead and now we will start creating. So let's first of all create our tree node. So let's create a binary search tree first of all. So search for left and right subtree. Yes, that's true, Shivani. Okay, so let's create our job first. Let's do our thing first. Whatever is the state later, I've created it here only, right? One thing, let me just do one thing. I will not name it BST Iterator, otherwise it will cause a conflict. I mean, it will only cause a conflict because it is a Java file. I'll just create a test. Okay, and I'll just create a test over here also. Now we'll create a class of BST Iterator. So class BST Iterator. We will work on this class later. Okay, so now let's first of all create our tree. So creating our tree. So let's create our tree. So let's say tree node, root node. Sorry, tree node. Tree node root is equals to new tree node. Okay, let's use the same logic. So the root is going to be 3. Okay, then we are going to do root dot left is equals to new tree node, which was 2, right? And root dot right is equals to new tree node, let's say 4. Is it clear? Is it clear how we are creating the tree over here? I'm just creating the same tree which was present in this example. It is clear, right? All right, great. Now let's try to reverse. Now let's try to do this out. Okay, so what we have to do is that we have to create an object of this BST iterator class. And being very honest, this question that I'm explaining you, this question has come to an interview of a very famous company. I'll not tell you the company's name because of NDA, that is non-disclosure agreement. So when you are in an interview, you are not supposed to tell people that what questions were asked in that interview specifically. But what I can tell you is that this question is asked in an interview at a very good company for a very good position for a package close to 20 LPA. And sadly, I was not able to qualify for this company despite answering this question correctly. But anyway, this is from a real interview experience. And this question can be really helpful to you in order to understand object-oriented programming as well. All right, so moving ahead. So what we have to do is that we have to create an object of this class. And using the object of this class, we have to iterate over this binary search tree that we have just created. And we have to create 2 methods. First method is called getNext. So getNext is going to return us the next smallest number in the tree. And then there is a next method called hasNext. So hasNext is going to return you a Boolean value, which basically checks whether that there is any next smallest number present in the tree or not. That is what is going to happen. So let's try to create it out. Okay, so a BST iterator must always take a tree node as root, let's say. Yep, it should always take, it should have a type of root as a property or as a parameter, class parameter. Then we will create a list of, why should I create a list? Yeah, I can create a list of it. List of integer list of integer is equals to node list. Okay, and then I will create a int index is equals to 0. Now I'll tell you what I will do. If I am able to extract all the information, like there are many nodes in the tree, right? So if I am able to like arrange all the nodes of the tree, or if I'm able to extract data from all nodes of the tree and store it in an ascending order inside this list of integer, which is basically like a vector in C++ or an array list in Java, if I'm able to store it in this way, then what will happen is that I have got an ascending order of all the nodes present with me. Then I can change the index on the basis of how many times the iterator has been called. So by default, it will be at 0. If the iterator is called for the first time, I will increment the index by 1 and then so on and on and on. Is the concept clear what I'm going to do? Did you understand what I'm going to do? Yes, no, anyone? If not, then I will explain you one more time. All right, I can see the audience members writing as yes. All right, great. Please explain one more time. All right, Twaran. So in BST iterator, what we are going to do is that first of all, we need that we need the BST or we need the binary search tree whose iteration we want to do. That is why I've created this tree node over here. The next thing that I'm going to do is that if by any way possible, I am able to iterate through every member in the tree and take out the data of this tree, then arrange all the data of this tree in ascending order, then technically my half of the job is done. Okay, so if I am able to arrange all the data of this binary search tree in a array list or in a vector in C++ and then sort it in ascending order, then half of my job is done, right? Half of my job is done. So if this iterator is called for the first time, then technically I am supposed to return the first value of this list, of this node list, and then increment the index by 1. If it is called by second time, then again I'm going to return the first element and increment the index by 2, or sorry, increment the index by 1 again. Isn't that what I can do? Yes, no, anyone? Is it clear this time? Bhavya had a confusion, and also we had a confusion from wait, I can't see. Bhavya had a confusion and Twaran had a confusion. So is it clear to both of you? Twaran is clear. How about you, Bhavya? Are you clear with this? If not, you can tell me. I'm looking towards my right hand side because I also have an external monitor where I'm looking at your chats. Okay, Bhavya, that's great. All right, so moving ahead, now let's try to solve this question. So now that we have an index at 0, now let's try to write a logic with the help of which we can find out the find out all the data and then arrange it in an ascending order. So in a binary search tree, there is something called Inorder. In a binary search tree, there is something called Inorder Traversal. This Inorder Traversal gives you the ascending order of a binary search tree. That is what it does. Now to explain what is Inorder Traversal, let me just come over here. Okay, so in a binary search tree, first of all, we always know that the left side is smaller, the right side is greater, and the parent is always in the middle of the left and the right. Is that part clear? In a binary search tree, left side is smaller, right side is greater, and the parent is always in the middle of the left and right. Is this part clear? Yes, no? Right? That is exactly what we are going to do. So in an in-order traversal, we always start from the root. But we always keep going to the maximum left that we can. We go to the maximum left, take that value, then go to its parent, take that value, then go to its right side, take that value, and then go back. That is how it works in a binary search tree. Let me just give you a better example by sharing my Google Chrome screen one more time. All right. So can you see my Google Chrome screen? Can you see my Google Chrome screen? Okay, great. So in this case, we all can easily understand that 1 is the smallest element in this case, right? So we will always start from 8. Okay, we will always start from the root node. Once we come to the root node, we will not store the value of 8. First of all, we will check, does 8 have any left side? If 8 has any left side, then we go to the left side. Okay, then now that we have come to 3, then again we will check, does 3 have any left side? If yes, then we will go to the left side. Okay, then we will check, does 1 have any left side? Then the answer is no. Then in that case, we will add the value 1 to the list that we have. That is the vector that we have, or the array list that we have. Once we have added that, then we will check, does 1 have any right side? No, it does not have any right side. So we will go back. Now we have come back. So we have already traversed the left side of 3. Now we will check, does 3 have any right side? Yes, 3 has a right side. Then we will come here. Now that we have come here, then we will check, does 6 have a left side? Yes, it has. Then it will go to 4. Then 4 has no left side. Then again, we will add 4. Then again, check for right side. No, 4 does not have right side. Again, coming back to 4, adding 6, going to 7. Then checking for left. No, no left. Then adding 7, checking for right. No right. Coming back to 7, coming back to 6, coming back to 3, then coming back to 8, adding 8, then going to 10. 10 has no left side. Coming back to 10, adding 10, going to 14. Then checking 14 has left side. Yes, 14 has left side. Coming to 13, checking for left. No, not there. Then adding 13, checking right. Right is not there. Coming back to 13, coming back to 14. 14 has no right side. Then and that is the end of in-order traversal. Did you get the logic of an in-order traversal? We always try to move towards the maximum left. Once we have reached the maximum left, only then we start the traversal in the right way. So this is exactly what in-order traversal is. So did you guys understand how in-order traversal works like? Yes, no, anyone? Okay. Can you tell me the in-order traversal of this tree in the chat box? Or not, let's say not this tree. Let's talk about this tree. Can you tell me the in-order traversal of this tree? Can you write this down in the chat box? Sir, if there are no children of child node, so maybe, so if there are no children of child node, so maybe count leaf nodes to take the binary tree, a strict binary tree. It is a skewed binary tree in that case. Skewed, S-K-E-W-E-D. If there are no children of child node, so we can count leaf nodes to build them. I'm not able to I think I misread your question, Manpreet. I'm not able to understand your question in the best way. Okay, I have a few answers in the chat box. Suryansh's. Okay, let me check. -4, 2, 3, 5, then 19, then 21, 25. Okay, that is fine. Yes, Suryansh, I think you have made a mistake. 25 instead of 25, you written 5 by mistake. Okay, no problem. 5, then 2, then -4. Great. Then it will come back to 2, and then it will go to 3. Okay, great. Then it will get back directly to 2, then it will get back to 5, then it will get back to 21, then 19, then get back to 21, then 25, then 21, then 5. Anmol, your answer is correct, but after 25, it will not go back to 21 and not go back to 5. So the last two are incorrect. Other than that, everything is correct. Okay, yeah, so great job. You guys have understood in-order traversal. So now if you have noticed, if you do the in-order traversal, don't you think you have gotten the all the values of the tree in an ascending order? Now notice that. Notice on what you have written in the chat box. Don't you think you got the ascending order of the tree? Yes, no, anyone? You got the ascending order. So that was our first challenge, to get the ascending order of the tree. So now let's write in order in code and then get the ascending order of the tree. So where is it? Yep. Sure. All right. So going to this file. Now let's write the ascending order. So before this, I'll just create a constructor, public BST iterator. I will write tree node. This dot node. This dot goes to this dot new, this dot node list is equals to new array list, right? And yep, this is what we will have. Now let's do an in-order traversal. So to create an Inorder traversal, I am writing a private function. So I'm not sure if you are familiar with private functions or not. Okay, there's something wrong over here. What is wrong? What is wrong over here? Move member into the class. Wait, just a moment. Write in the constructor once again, public DST iterator. So I can do a tree node root. What is the problem? Can't really understand it. Who member inside the class? What am I doing it wrong? It is already inside the class. Just allow me 1 minute. I am not able to understand what this error is. Okay. So I have to create a constructor over here. Oh, it was because of the function I had written after this public BST iterator. Tree node root. Okay, this dot root is equals to root, and this dot node list is equals to new array list. Okay, now let's write a function to create a Inorder traversal. So private void Inorder. Okay, so for this, what we will do is that this thing. We need to have a tree node for this tree node. Okay, let's try to write Inorder traversal. So first of all, we know that in an Inorder traversal, we always go to the left side. Then we come to the parent, and then we go to the right side. That is what we do. So first of all, we must check if node is not equal to null, because it is very well possible. If tree node is not equal to null, if it is not equal to null, then I will do an Inorder traversal in order of tree node dot left. Once that is done, then I will do node list dot add. Then I will write tree should be tree node dot left. No, it should be tree node dot data. That is what it will be, and then I will do an Inorder traversal of tree node dot right. Are you able to understand this recursion? Private is not visible to main. No, private is visible to main. Private will be visible to main if it were in the same class. But in this case, this private will only be accessible inside this code block, not anywhere outside or inside, not anywhere outside it. If we have to get ascending order, then we have to take in order for that BST. Yes, that is what we have to do, and that is what we are doing. Okay, so this is the Inorder traversal. Are you able to understand this Inorder traversal? Did you understand this Inorder traversal? Okay, great. So this is how Inorder traversal works. So now that our Inorder is done, we have added all the Inorder traversal in this case. Now, just to show you that it works, let me just show you that it is working. Yep. Let's say print public, public print, public void print. Okay, so we will just print SOUT this dot node list. But every time you create a object of BST iterator, we want this in order to work. So what we would do is that we'll just call in order over here in the constructor. And once we call it, we will just pass the tree node which we have created. So in this case, it will be root. Okay, so every time you create an object of BST iterator with this constructor, this will automatically be executed. That is what it means. Okay, so moving ahead, this is, what is this thing? Do we need it? No, we don't need it. So I'll remove it. I don't know what's wrong with my IntelliJ today. Yep. So this is our main function. Now that we have a tree node present here, let's create a BST iterator. Iterator is equals to new BST iterator with the argument as root. And then let's do iterator.print. Okay. So let's run it. It will print you 234. It should print you 234. Let's see. Yep, it is printing 2, 3, and 4. So definitely we are able to do this in a ascending order. And now let's see how we can implement the get next and has next. Okay, so let's do a get next. So it will be public boolean get next. So in get next, what we will do? Let's first check if there's a has next or not. Public int has next. So has next will be something like this. If node list is not empty, if node list is not empty, return node list dot size, which is greater than, index. Wait, what am I doing it here? It's greater than index. Sorry. This is my mistake. It should be boolean over here because has next has to be a boolean and get next has to be an int. Yeah. So this is what it's going to be like. Yes. So otherwise return a false. Okay. So this is how we are going to check whether the iterator has the next property. So if the index becomes greater than the size, then there is a problem, right? Then and only then there is a problem, which is not what we want. So that is the only case that we have to check. Otherwise, in get next, what we have to do is that we'll have to just check a has next. If has next is true, then we are going to take out the last element. Element is equals to node list dot get index, and then we are going to do index plus plus, and then I will just return the element. Okay, if this is not true, then I will, let's say, return -1. If -1 is coming, that means the element is not there. Okay, now let's try to call this out. So I will just do system.out.println iterator.get next. Then I will call it 4 times, let's say 1 time, 2 time, 3 time, and 4 time. Okay, now let's run it and see what is happening. Yep, this is exactly what we wanted. So we are able to create an iterator class just for BST and then get every single time the next smallest number in the BST. And this was my question. And this with this question, my foundational class for today is over. So if anybody has any questions, you can very well put them in the chat box or in the Q&A. So any questions, anyone? Why to use this, sir? Why to use what? Okay, this. Do you mean this keyword, THIS? Is that what you're saying, Anmol? Is that what you're saying, Anmol? I'm not sure, but just making sure about it. Binary search tree. Okay, so are you talking about this place? This that I have written over here? The ones that I've highlighted? Then which one? You can tell me the line number. Or do you want me to ask that? I'm not exactly. Why to use BST? Okay, why do we use BST? Okay, we use BST in a lot of ways because it helps us to reduce a lot of extra space. because there's always a parent-child relationship over here. So in a parent-child relationship, what happens is, let's say there are two children which have the same parent. So in order to fetch the information of a child and parent, you can just have one parent and multiple children. So that exactly helps you to save space by not creating the copies of parent multiple times. Being a C++ user, the logic of iterator is not clear to me. Okay, so Dharya, what exactly happens is in an iterator, so there is always an iterator basically means something that iterates. So that is exactly what is happening. So let us say you have a vector. And if you want to print all the numbers of this vector, okay, then what do you use? You use a for loop probably. Is that right, Dharya? Don't you use a for loop? Don't you use a for loop? Yes, no? Yes, you use a for loop. You use a for loop. So this for loop is going to iterate through every element inside this vector and is going to print it. The same is the logic with iterator as well. So iterator checks consistently that if there is a next element, then I should be able to go to the next element and do the logic that whatever the user has written. In your case, the logic is printing that element. Okay, so that is the exact concept of iterators in Java. The iterator concept also exists in JavaScript and also in Python. So the concept of iterators is something that I think every programmer must know. I hope it is more clear to you now, Dharya. So, sir, BST is very vast topic. Would you suggest some resource to cover it? You can definitely check that out in any coding ninjas course as well of data structures and algorithms. Apart from that, there are some good books also. There are some other platforms also. Maybe we can talk about it on LinkedIn. I already had posted my LinkedIn ID last session. If you want it again, I will post it again by the end of the session. So the concept is clear, but still unclear on how I will personally be able to code it in C++. You can basically code it in C++. You just have to create this thing, a struct or a class in C++ also. The major reason why you are not able to create it in C++ is only because your concepts in C++ object-oriented programming is not very clear. In Java, there is no chance that you can work without class, but in C++ you can work without classes as well. That is the only reason why you're having issues in thinking how you will code it in C++. Whereas in Java, there is no chance. You cannot work without a class. It is a mandatory thing. You cannot work without a class. In C++, on the other hand side, you can work without a class. And that is the only reason probably because of which you're having issues in trying to understand how you will code it in C++. Because in C++, the maximum that we do is that we write the header, we write int main or void main, and then we write all the code in the same place. Right? We create no classes. We create no static type, private type, anything. We are just concerned about key. Our job should be done. That is what we are concerned in C++. But you can use the concept of classes in C++ also to get the job done. So do empty leaf nodes are count in BST or in strict BST? They are counted in BST definitely. If empty leaf node, no, there cannot be an empty leaf node. A leaf node basically means that data is there, but left and right children are not there. Can you explain how graph and tree are different? Yes. So in a graph and in a tree, there is the relation is always from parent to child. Okay, but in a graph, the relation can be from parent to child as well as from child to parent. So it can be both ways as well. And a tree is very well, I mean, a tree can have parent-child relationship, and there's always less than one parent. There's always at most one parent to a child. In a graph, there can be multiple parents to a child. A child can also be a parent to its own parent. There's a very complicated structure in graph. So graph is definitely very, very different from tree. Any more questions? Seems okay. Seems like there's no more questions. So I think we are good to go. Okay, one last question. Can we do the same question with the concept of graph? Yes and no, probably not. Because if the question is of undirected graphs, it will not be possible.